So we're going to present this what we call the plane stress problem. It's usually a reference to explain the finite element method, and in fact the direct stiffness method. And in this case, the variational formulation. We have a not so simple problem, but a quite interesting problem because it's a bidimensional problem. So this is usually a reference for this presentation. Okay. Now we have done something in using a bar element, which is quite simple. But the elements we have seen here in this variational formulation in the bar element are the same we are going to find here, with a much more complex expression or matrix expression and so on. So let's go to arrange this plane stress problem from the variational point of view. So in fact, we're going to do the same things as in the bar element, but in a much more complex problem, just to explain how it works. So we consider this the plane stress problem when we have a problem like that. For example, considering a plate. This is a plate. A plate is a domain topology where the thickness, or in general transverse dimension, is quite much smaller than the in-plane dimensions. So we call these in-plane dimensions, x and y, is the plane where the plate is placed, and usually the thickness, we consider it is in the z direction, and we consider this plane stress problem when this thickness is quite smaller than any of these in-plane dimensions. Okay. In this plate typology, we consider the midplane, the plane which is placed in the midpoint of the thickness, and we are going to arrange all the magnitudes to this midplane. Okay, so all of them are referred to this midplane reference, and so as to neglect the thickness dimension. Okay. So this midplane will represent the behavior of all of the plate. The domain, again, is divided in the internal domain, we call it omega, and this boundary domain, we call it tau, where we are going to place the boundary conditions. In the bar element, it was very simple because we have two nodes, initial and final node, but now it's a bit more complex because we have a curve usually where the domain or the boundary conditions are placed. Okay, so this is our plane stress problem. Look, there's loads are applied in the in-plane, in the mid-plane. So we don't have loads applied in the normal plane of the plate. This is our plane stress problem. So we're going to make some physical assumptions to consider our problem as a plane stress problem. For example, we consider this plane is flat, and this mid-plane is a symmetry plane for the thickness. So the geometry is symmetric with respect to this mid-plane. The loads and the support conditions and everything are symmetric with respect to this mid-plane. So we consider, this is why we consider this mid-plane as a reference, and all the behavior of the plate are placed in some way in the mid-plane. So any point of this mid-plane will represent the behavior of the plate in the normal direction. All the points placed in the normal direction of this point, placed in the midplane, behaves in the way the point in the midplane does. This thickness dimension is much smaller than the in-plane dimensions, any of them, about 10%. We expect that this thickness is less than 10% of the smallest in-plane dimensions, and the displacements, strains, and stresses are considered as uniform through this thickness. So this is the which reflects the importance of this thickness as a small dimension. We consider that these magnitudes are uniform through the thickness. If the loads are applied in the mid-plane and everything is symmetric with respect to this mid-plane, we consider that these transverse stresses are 0 or negligible. So in fact we set these stresses to 0. So any of these three components of this stress tensor is set to 0. So we are worried only about the magnitudes that work in the xy plane. Okay. This is the physical assumptions for plane stress, and additionally, in this course, we consider that this plate is fabricated of homogeneous materials. We consider this material as homogeneous through the thickness. So we don't have this change of materials through the thickness, just to simplify the solution of the problem. So what happens with these stress and force displacements in this in our plates? And same thing we have done with the bar element, that's defining these magnitudes. So we are going to talk about the internal forces applied in this mid-plane. Look, these internal forces here applied in the mid-plane. So everything is considered as a mid-plane. So these internal forces will represent all the thickness, this thickness with value h. So these internal forces represent all the thickness. The in-plane stresses, again, are considered along the thickness. So with this positive, with this sign convention, the strains again are considered in this way. So xy axis. So we have this strain in y direction, in x direction, and this distortion here, xy strain along the thickness. And the displacement, again, we consider these are the displacements along the thickness, and as we said, these magnitudes are considered uniform along the thickness. So this displacement here is the same for all these points along this vertical or z direction along this thickness. Okay? So if we consider this as uniform, to simplify the problem, this is the notation and this is the sign convention again. The plane stress boundary conditions are considered like that. So this boundary domain, we call it tau, are divided in two parts. One, this is the displacement boundary domain, where the displacements are prescribed. Well, prescribed is equal to 0 or equal to the prescribed displacement. And we have a boundary condition which we call tau sub t, where tractions, boundary forces are applied. So we can have all these boundary conditions, displacement and tractions. This decomposition of the boundary domain has sense in the finite element formulation of the forces. So we divide these two domains to take them into account in the formulation of the finite element equilibrium forces. So we can have as well stress boundary conditions, which is the tension applied in the boundary condition in this element here. We have a normal and tangential component from the stress along the thickness, where we consider this stress as a constant value. So magnitudes and boundary conditions, and our given problem data will be the geometry, of course, the material properties. We consider this as homogeneous along the thickness. The applied forces and the boundary conditions. These boundary conditions include the boundary forces or interactions. Boundary forces are acting in the body force, in the body of the plate. Interactions are forces acting in the boundary domain, and this prescribed displacement, usually in this boundary domain, tau sub u, we have explained before. Our problem consists in find this in-plane displacement. Above all, we must get this in-plane displacements. We want to know the in-plane strains and stresses and internal forces, but take into account that these magnitudes are displacement dependent. So if we find this displacement, so we are going to find everything, because this is our primary variable, the displacement function all over the plate. Well, this is some matrix notation. we had just one displacement, one-dimensional problem in the bar element. Now in our two-dimensional problems we have displacement in x direction and y direction. So here we have these two components of the displacement. So we have two unknowns for any point. This is again continuum formulation. We are in the continuum plate for now. So we are going to talk about this displacement for any point x, y in this x direction and y direction for the displacement, two components. The strain, once we have neglected the vertical strain, these are the strains in the in-plane dimensions, so x and y strains, and this distortion here in x, y component. This too is to simplify the dot product of energy. Remember the 1/2 here. So this is just convention to write this strain deformation here with these two value, just to simplify the calculation of the energy. And the stress, again, according to these three components of the strain, we have stress in x direction, y direction, and this tangential stress, which are all of them depending on the point of the plate we are working. So all of them are x and y dependent, and they don't have set dependence because we are neglecting the behavior of these magnitudes along the thickness. We consider them as a uniform along the thickness. Okay. What happened with this strain here? This is an important point. Look here. What happens with this vertical strain? In fact, this vertical strain is not zero in general. Which is zero is the set stress. So vertical stress is zero because we have application of the forces in the in-plane dimensions. This strain, because of the Poisson effect, is not zero, but in energy terms, this dot product with the z strain and z stress is equal to zero because of this assumption with the vertical stress. So even if this vertical strain is not zero, the term in the energy in the internal energy is zero, so we are not worried about this vertical stress. Okay, vertical strain, sorry. Well, those were our magnitudes, strains and stresses and displacement, and now we have the governing equations. Well, the governing equations are the same governing equations as in the bar element, so we have a similar Tonti diagram which is equal for any problem. This is what I wanted to say. We have the same steps trying to solve the problem. The point is now we have 3 components for stress, 3 components for strain, and 2 components for displacement, but the governing equations are the same 3. First is the kinematic equations, which relates the strain and the displacement using this derivative operator here. So these 3 components of strain are related with these 2 components of displacement, which are the ones we are worried about in the plate problem, in the plane stress problem. We have a constitutive law which relates the stresses and the strains. We assume the linear elastic theory, so these 9 components of this matrix will be the ones according to the Hooke's law relating stress and strain, and these are the constitutive law. And we have the equilibrium equation, same in the bar as in the bar element, which relates these derivatives of the stresses and these body forces. Bx and By are the body forces per unit of volume acting in the plate. So equilibrium forces, equilibrium equations, kinematic equations, and constitutive law are the 3 ones which in matrix form have these expressions here. So these are the same governing equations we had in the bar element in the same Tonti diagram. The elastic matrix, assuming the Hooke's law, which relates these stresses and these strains, are these ones. So this is known for the plane stress problem. And here we have this Tonti diagram of the governing equations, where the yellow squares are the unknowns, and the red ones are the data, the problem data given to solve the problem. Again, we have the displacement as a primary variable related with these strains using these kinematic relations. Same equation we have just seen in the last slide. Relation between strains and stress are the constitutive law in all the domain, and these three squares are the three magnitudes we wanted to find to solve our problem. And for that we have these body forces, which are forces applied per unit of volume, these prescribed tractions and forces applied in the boundary domain. So these are force boundary conditions. Here we have the same expressions here, where n is the normal vector to the boundary surface, and we have prescribed displacement in the boundary, in the displacement boundary tau sub u. So displacement boundary conditions which prescribe some of the displacements unknown in the problem. So if you see, we have the same scheme with the same Tonti diagram for the governing equations. We call it in the strong form. This strong form, let's see, this Tonti diagram with assuming the strong form, which means that these governing equations must be accomplished at every point of the domain. So at every point of our plate, these equations must be accomplished, point by point, which is not the same as the weak form we're going to see here, which implies a quite important difference, because take into account that this weak form implies the total potential energy principle. What we do in this total potential energy is an integration of these governing equations. So we are calculating a sort of average of the energy of all the domain, not considering what happens at point by point at every point of the domain. So we are making a sort of integral, which means where we are solving a problem in a weak form. So we are not finding a solution at every point of the domain, an exact solution at every point of the domain, because we are using a total potential energy which implies all the domain of the plate or the ball element or whatever. This is a quite important difference between the strong form and the weak form. So this weak form assures us that in the integral, as an integral, we are getting to the exact solution as an integral, okay? Which is a weaker form to solve the problem we are trying to solve. Tonti diagram is same scheme, but here in the equilibrium we have here. Let's see. Well, here in the equilibrium, this blue square shows the minimization of the total potential energy. This is our equilibrium condition, because our total potential energy principle states that this is the condition to get the exact solution, but we are going to get an exact solution that minimizes this total potential energy, which involves all the domain. We are not solving the problem point by point. Same thing with this minimization of the external work. These force boundary conditions here, the external work, is one half of the total potential energy. So we are calculating this variation of this total potential energy equal to 0. So this is a condition, is our condition to solve the problem using a weak form. So we are not getting a solution point by point, so we are minimizing this total potential energy, which affects to all the domains. This is the main difference between the weak form and the strong form. It's much more difficult to get the solution to the strong form, much more difficult. In fact, usually for the finite element modeling, finite element formulation, we get the weak form using this type of potential energy minimization. Okay. Well, again, we're going to make similar assumptions now, but using a much more complex problem with 2 components of displacement and 3 components for strain and stresses. So we are going to talk about the internal energy and the external work. This internal energy again is calculated like 1/2 of this integration, the stress times the strain. Now the stress and the strain are matrix, are 3 component vector. In fact, they are 3 component tensors, but we use a vector simplified notation to get this internal energy times this h. This h is the thickness. So this 1/2 h stress and strain is the internal energy per unit of volume. So we integrate this internal energy all over the volume and we get this internal energy. This stress, we said, this stress can be expressed using the Hooke's law, using an elastic matrix times the strains. So we can change this stress matrix by its expression using the elastic matrix and the strain here using the constitutive law. So finally we express this internal energy in this way. And external work considers these body forces. These body forces are forces per unit of volume times the displacement along the thickness. We consider them as a uniform along the thickness, so you multiply this external work times h, and we integrate along the volume, plus the boundary tractions applied in the boundary part of the traction boundary conditions. So this vector times the displacement will give us the external work times the thickness, because we are considering this as uniform along the thickness. So the addition of these 2 integral values are the external work applied to the plate. So this external work, this internal energy, lead us to the minimization of this total potential energy, which is calculated in the same way. This principle states that the solution of the problem satisfies these governing equations when this total potential energy is lead to get stationary form. So we must get these displacement values which render this delta equal to 0. So we want this variation equal to 0, and the displacement function which gets this variation equal to 0 is the solution of our problem. Take into account again that we are talking about a displacement function. So we are talking about total potential energy all over the domain. We are not worried about what happens at any point of this plate, but what happens in the total value, total integration of this internal energy. So this is the point with the weak form of the problem. We must do it with respect to any admissible variation of this displacement function of the exact displacement solution. Okay? Taking into account that this delta U must be an admissible variation. This admissible variation implies the continuity and the boundary conditions in the plate. So again, that was the formulation, the total potential energy principle for the continuum space. Now we're going to jump to the discrete space. This discrete space means that our continuum domain with this body and this boundary are discretized in a finite number of elements. Any of these elements will have a body domain and this boundary domain where tractions and forces will be applied. This element, we haven't said anything about elements. Take into account that this element could be a triangle, a quadrilateral, anything. So this is not non-element dependent. This is a variational formulation for all the domain, and then we are going to worry about these elements. So this is general. This is not for one element or one-dimensional element or two-dimensional. No, this is a general formulation. This is for the plane stress problem. So this plane stress problem could be solved choosing one of these plane elements but this does not worry us now, because we're worried about this minimization of this total potential energy. And again, this variation of this total potential energy, taking into account that this potential could be expressed as an addition of the total potential energy from any of these discretized element, from 1 to n super e, number of discrete elements. So this variation, the variation which of the total potential energy, which must be 0, will be the addition of this contribution of any of these elements. So if we assemble these contributions of all of these elements, we get the total variation. So to assure this result, we must assure that any of these contributions of the variation of the total potential energy must be 0. Any of these contributions delta P for any element includes the internal energy and the external work over this element. So finally, if we consider we are in the element level, we are talking about elements, this finite element, which can have n nodes, we said nothing about which kind of element we are talking about. This is non-element dependent. So consider, for example, 4 nodes. Any of these nodes will have nodal displacement values. So we consider 2 components of the displacement values for any of these nodes. So our displacement vector will have 2 times n, in this case 2 times 4 components, considering these 2 components x and y for any of the nodes involved in the finite element. We want to explain the displacement function, the continuous displacement function, using these nodal values of the displacement. So we are going to use an interpolating functions, call it shape functions, n 1, 2, 3, same number of shape functions as nodes, so we will have n shape functions, and we are going to place these shape functions in this way. We have this matrix involving these shape functions, then this continuum, let's see if I can, this continuum function of displacement here in the right, in this yellow square, this continuum displacement function can be interpolated using this shape functions matrix times this nodal here, this nodal vector, considering these nodal values of the displacement. So we jump from the continuum function to a discrete function using these interpolating functions, and in a more simple way we can express this displacement with a matrix expression n times u e for any element, taking into account that this shape function is corresponding to one of the nodes here in the element. We assume the interpolation for both components are the same. Usually x and y have the same interpolating functions, so we assume the same values for any of them. And these shape functions must accomplish some conditions. Later we're going to talk about a bit more about these conditions of the shape functions, but for now we can advance that these conditions includes the interpolation condition, which means that every shape function must take a value 1 at the node. Remember that any shape function corresponds to one node, and 0 at the other nodes, all of the other nodes of the element. This is the first condition. This shape function must be continuum between the element, inside the element, and with the elements next. And the completeness conditions, which affects the requirement for consistency and convergence. Consistency and convergence are 2 requirements of the finite element modeling, which reclaims this completeness condition. So I think in the last class, class of the course, we're going to talk about this completeness and these continuity conditions, which assure us consistency of the results and above all the convergence We are very worried about this convergence. We want to be sure that if we get a finer and finer mesh, we are getting to the exact solution. This is what convergence assures us, and to get this, completeness is one of the requirements of the shape functions. Okay. Well, if we get the shape functions, again, we have the displacement interpolation in the discrete space. Now we want to get the strain displacement discrete expression, and we get this using the derivatives of the strain. Remember that this x strain and y strain are the derivatives of the component x and y of the displacement, and the cross strain, the strain x and y, the distortion, is the cross derivative between the displacement x and the displacement y. So if we apply these kinematic equations, these derivatives, to the displacement interpolation, remember we are here, we are in this displacement expression, in the discrete expression, the one in the right. This one in this discrete expression, if we apply the derivatives, we don't get mad. Okay. If we apply the derivatives to this matrix expression, we get this matrix which involves the first derivative of the shape functions with respect to x and respect to y. This is what we call, again, the strain displacement matrix. It's the same strain displacement matrix we got in the bar element, but with two components of the displacement and three components for the strain. That's a much more complicated matrix, but the concept is the same. The idea is the same. We relate this strain vector, three components, with the nodal displacement using this strain displacement matrix V, calculated from the derivatives of the displacement, in fact, of the derivatives of the shape functions used to interpolate the displacement function. In this case, this B strain displacement matrix has an order 3 per 2 times n, where n is the number of the nodes of the finite element, or the element, discretized element. Okay, so now we've got all we need. So we define this total potential energy in the element. This internal energy will be 1/2 h stress time the strain. This is for 1 unit of volume. We integrate all this internal energy along the element. So we get this expression 1/2 integrate h times strain times elastic matrix times the strain, and we get a number which is the internal energy of this element. And we have all of this. We have this strain and this elastic matrix. They are known. The strain is calculated like that using this B strain displacement matrix. So imagine that we get this integral, and this is the continuum expression. We get to the discretized expression, and this strain displacement gets this strain displacement matrix times the nodal values. The nodal values vector is out of the integral because they are constant values. So what we have in the middle is the stiffness matrix, which has a very similar form like the one in the bar element. We have integral the B strain displacement matrix, which are in fact the derivatives of the shape functions transposed. Then again the same B matrix with the derivatives. In the middle we have a relation between stress and strain. In the bar element it was the axial rigidity, but now it's a 3 by 3 order 3 matrix with elastic matrix. And we have this H, which is the thickness, because we have assumed that this behavior is uniform along the thickness. So this integral must take into account this thickness. So we have this integral, this constant value integrated along the thickness, so we must multiply it by H. So this is the expression for the stiffness matrix in a plane stress problem, which I insist. It has the same form, similar form, includes the same ingredients as the one in the bar element explained before, and same thing with the consistent nodal force vector. Now, point is that we have body forces and traction forces. This is the continuum expression for the external work, but now we have discretized these expressions these values, these displacement functions are expressed like a matrix, shape function matrix times body force. This body force is a vector. Traction, same thing. This displacement are expressed like matrix, shape function matrix times the nodal values. So when we calculate this integral, these nodal values come out of the integral, and what we get in the right side is the consistent nodal force vector, which comes from the external work, which includes the body forces and the surface tractions. This is the one in the discrete field. So this is continuum expression, this is the discrete expression, which lead us to a consistent nodal force vector, which is consistent because it comes out from the total potential energy principle minimization. Okay. Remember that these body forces are applied in the body all over the domain, while the surface tractions are applied in the boundary condition. Now we are talking about the boundary condition of an element. So this is a bit different because it's not the boundary condition of the plate, it's the boundary condition of the element. Okay? So now we have to consider the forces between elements as a surface tractions of acting over this element. Then in the assembly step, these surface tractions will vanish if we are talking about the elements inside the domain. So these surface tractions will vanish, and the prescribed displacement will be applied only after the assembly, but only in the displacement boundary condition. So now, finally, we get to the same thing. We have an internal energy, we have a external work, we have a variation of this total potential energy, and if we make these derivatives, we have to calculate this variation. Look at this, this 1/2, it disappears because we have calculated the variation of the total potential energy. Lead us to this expression here. See, here we have this expression here. This is for an arbitrary variation of the displacement nodal values. So if we want this to be 0, we must assure that this term inside the brackets is 0. So this leads us to an expression similar, equal to the one we had in the bar element, which relates the nodal internal nodal values and the consistent nodal force vector in this in the nodes of the discretization of the element, related using this stiffness matrix K, calculated as we saw before. So this is the element stiffness equations for this element. So we assemble these equations for all the domain, and we get the equations to solve the problem. So we got to this solution using a variational principle, which is the minimization of total potential energy. We got to the same place. But the point is that this stiffness matrix is calculated in a different way, but using the same idea. Okay? That was for the plane stress problem. Remember, this plane stress problem assumes that the vertical stresses are 0 because the loads are applied in the mid-plane. So we have vertical strains, but we have no vertical stresses because we don't have these loads. And we have a sort of twin problem for the plane stress, which is the plane strain problem, which is quite similar. But now, imagine that we have a domain which is equal in the same direction, z. So now z, this z direction, is the one here. This is the cross section. But we have a domain which is continuous, which is equal in this z direction. So we can consider this problem as a plane problem, considering one section here with this load. So where the geometry and the load remains constant along this z direction, we can treat this as a plane strain problem. The point is that if this geometry and load are like that, accomplish these conditions, we can consider that this strain along z direction is 0, these components are 0 as well because of the symmetry, the stress in z direction will not be 0, but the strain, the z strain is. So we have in sort of the opposite consideration, the opposite hypothesis between stress and strain than the plane stress problem. So if we consider these assumptions, strain assumptions, we go to the Hooke's law, the elasticity law, and we can neglect these terms. We can neglect these terms, and we can get a relation between these stresses. So imagine that this is equal to 0. So we have a relation between this z stress and the x and y stress. So in fact, our components of stress are the x and y normal stress and this sigma xy, but not the sigma z, because it is defined in terms of the x and y stresses. So our real components of stress are these three, the same as in the plane stress. The elastic relation between these three stresses and strains are this elastic matrix, which is not the same like the plane stress. It's a variation, and in fact it's the only variation we have between the plane stress and the plane strain, this elastic relation between the stress and the strain. Okay, because the component of displacements, strains and stresses are exactly the same. Both problems have the same components, so we can treat them in the same way. In fact, the development we have done with the variational formulation, it's the same, and we of course will get the same results. The only thing that varies is that the relation, the elastic relation between stress and strains, are corresponding to the strain assumptions. These are the strain assumptions. So the elastic matrix is different, but the treatment of the problems is the same. In fact, when you implement a finite element program, you implement the plane stress, and you don't implement again the plane strain, because you simply have to change this elastic matrix. If you change the elastic matrix, you can treat the problem with the same implementation, taking into account that this vertical, not vertical, but z stress is determined and dependent on sigma x and sigma y, as I said, and the Hooke's law leads to these expressions between the strain and stresses. So if you implement the stress problem and you change the values of elastic modulus and Poisson coefficient, you change this using this expression here, you can treat the problem as a plane stress or as a plane strain simply by changing these elastic constants to change this elastic matrix from the plane stress elastic matrix to the plane stress elastic matrix. I think this is one of the assignments you have, just to verify, just to get this relation between the elastic constants in the plane and the plane stress, just to make the same implementation. Of course, the variational formulation leads us to the same place, and this is the plane strain problem summary. These are the assumptions, the relation between strains and stresses. These are the stresses relation. We have sigma z related to the sigma x and sigma y, and these are the relation between stresses and strains using these elastic constants modified for the plane stress. So we can treat this plane strain problem as a virtual plane stress, simply changing the mechanical parameters, because all of the rest is the same: components, strains, stresses, governing equations, and so on. This is the usual treatment of the plane stress problem, which is quite common in simple simulations for with a finite element. And I think this is everything for now. So finally, we have done for the plane stress problem this same variational formulation to get the same result, to get the governing equation, to implement the governing equations, and to get to the discrete equation system to solve the problem and to get the solution in the nodal values for displacement, our primary variable, and from these nodal values get the strains and the stresses in the para-element problem, one-dimensional, and the two-dimensional problems. Now we can do the same thing for three-dimensional problem of any problem you can imagine. So it's a question of defining which are your components, your unknowns, you are given problem data, and your physical assumptions, and make same steps. This is the method, not the method, but the variational formulation I wanted to present now as a basic step in the finite element modeling. In the next classes, we're going to talk about how we treat this implementation, this formulation in every type of element, and above all, we are going to talk about which are the advantages of using this variational formulation. Okay? Is there any question, any comment, anything? Well, as I told you, you will have your assignments and the bibliography and everything in, I hope, in 10 minutes, maybe 20 minutes, in that direction. And I hope this week the virtual center of FINME will be arranged and everything will work. Okay. Next Monday, more finite element.